In this video, you'll learn how to control several DC motors with encoders using a microcontroller. In my last video, I showed you how to use the PID algorithm to control a single DC motor. First, we connected a microcontroller, motor, motor driver, and encoder in a loop. Then we computed the control signal that is used to direct the motor to move to a target position. If you aren't familiar with PID control of a single DC motor, I suggest watching that video first. In this video, we'll start by connecting two motors to a microcontroller. Then, we'll update the control code so that it can work for as many motors as you need for your project. In the last part, we'll coordinate 4 motors to move our differential drive robot. There are plenty of microcontrollers out there that will work for this project. I'm using a Pololu A-Star Mini SV because the built-in regulator can tolerate input voltages between 5 and 40 volts. I'm using a pair of powerful VNH5019 motor drivers because their high current limit allows rapid direction reversals without triggering overcurrent protection. To complete the system, I've added two 12-volt Pololu DC motors with encoders. To power the system, I've connected 10 1.2-volt nickel metal hydride rechargeable batteries in series to make a 12-volt source. Here's the full connection diagram. Yes, I know, it looks like a bit of a mess. Let's break it down. Start by connecting the control signals for the motor drivers. Be sure to use a PWM pin for the PWM input of each motor driver. Next, connect the encoder outputs to your microcontroller. Make sure that the first output from each encoder is connected to an interrupt pin. Now, connect the ground of the motor drivers and encoders. Also connect the 5-volt logic supply from your microcontroller to your peripherals. Power the motors using the outputs of the motor drivers. Finally, connect the battery or other appropriate power supply to your microcontroller and motor drivers. Looks like I'm almost done with my connections. Here I'm connecting the 5-volt logic supply to my microcontroller. I've soldered all the 5-volt wires together using this handy solder seal wire connector and a heat gun. Now I'll connect an input pin to the motor driver and an encoder output. Phew! Oh, and here's my 10 1.2-volt batteries underneath. With the system connected, we're ready to update the position control code. First, we'll move the PID control code into a class so we can reuse it easily. To complete the class, we'll need to define PID parameters, have methods for setting the parameters, and a function that computes the control signal. These private members are the PID control parameters and storage variables for computing the integral and derivative. I'm writing the default constructor with an initialization list. This automatically sets the values of the class variables anytime an instance of the class is created. The setParams function does exactly what you'd expect. The variable umax sets the maximum power to be written to the motor. Usually that's 255. The evalu function computes the control signal using the code I wrote in the last video. I just need to make a few edits to the names of the variables after copy-pasting that code in. Now we need to write pin definitions for multiple motors. Here I'm using constant integer arrays to define the pins I connected to the 2 encoders and motor drivers. However, if you had more motors or drivers, you could simply append their pins to these arrays. Here I'm creating 2 instances of the simple PID class in an array. That way I can loop through the array when I compute my control signal. This makes it easy to vary the number of motors connected to the system. The last important change to the code is updating the read encoder function so that it can be used for more than one encoder. To do this, I'll convert the read encoder function to a template function with a template parameter j that is the index of the encoder. Here I'm using the template parameter j to read from the correct encoder pin and increment the correct position variable. If this template function is called with index 0, the compiler will create a version of the function using the index 0. If called with an index of 1, then another version of the function is generated with the template parameter j replaced by 1. Now I'll attach 2 interrupts, one for each encoder. Notice that I use the read encoder function with the template parameter that corresponds to the index of the encoder. That way each encoder gets its own read encoder function that will increment its position. There's a little housekeeping left. In the setup function, I'm setting the pin modes for the encoder and driver pins. I'm also setting the PID parameters. I'll set one target for each motor in the loop function. To safely access the position variable that is updated in the read encoder function, I'm using an atomic block. Finally, it's time to loop through the motors, compute the PID control signal for each, and then signal the motor drivers. Oh, and don't forget to include your libraries. Here's the code in action. The two motors follow the target reasonably well, but could probably use some parameter tuning. If you're using a large microcontroller with a lot of pins, you can connect any additional motors to your remaining pins. I've opted to use two smaller microcontrollers with the same connections. This minimizes the number of interrupts that occurs on each controller. To coordinate movement, the two controllers communicate with each other using I2C. In I2C, there are two types of devices, a main device I'm calling the leader, and peripheral devices I'm calling the followers. To connect using I2C, connect the SDA and SCL pins from each microcontroller. I've added code to the leader that sends the appropriate target positions to the follower. When the follower receives the message, it uses the received target. The leader will also ask the follower for its current position. When the follower receives a request, it sends its position back. Notice how the leader controls the communication, while the follower only receives information and responds to requests. To coordinate all four motors, I've created global target arrays with 4 elements. There's a float version to avoid rounding errors. Now I'll write a setTarget function that defines all 4 target positions based on the current time t. Rather than defining the targets directly as a function of time, I'm specifying a position change and then updating the float target global array at each iteration of the loop function. With the target updated, I'll convert it to a long so that it can be sent to the follower microcontroller using the sendLong function that I didn't show in this video but has been added to the code. Inside the loop, I'll call the setTarget function to set the target. Here's the code in action. Whoops, looks like the wheels are spinning opposite directions. To fix this, I'll change the target direction on the last 2 motors. That's better. So far I've only set the target in terms of encoder pulses. To set a rotation or distance target, I need information about my system. My encoder records a maximum of 64 pulses per rotation. This code only uses 1 out of every 4 pulses because it only triggers when encoder A rises. So I'm recording 16 pulses per rotation. The gear ratio of this motor is 18.75 to 1, so that means there are 16 times 18.75 pulses per rotation of the output shaft. The wheels have a circumference of about 28 centimeters, so I'll divide the pulses per turn by 0.28 meters to get the number of pulses that will occur per meter of travel. Let's see if I did my math right. Here, I'm setting a velocity target of 1 rotation per second. Then, I'll compute the target position change in pulses by multiplying the velocity by the amount of time that passed since the last iteration of the loop, and how many pulses occur per each turn of the wheel. The result is how many additional encoder pulses are needed to maintain the target velocity. Here's the code running. Watch as the yellow marker passes once per second, because I set a target speed of 1 rotation per second. This last bit of code sets a repeating pattern. Do nothing for 4 seconds, move forward for 4 seconds at a speed of 1 meter per 4 seconds, and then move backward at the same speed for the next 4 seconds. The pattern repeats because I've computed the modulus of the time variable. The yellow tape marks 1 meter. Now we travel forward 1 meter at a constant speed and then backward at the same speed. I hope this video helped you to understand how to connect and write code to control several DC motors. Let me know if it did and how you applied it in your project in the comments below.